London dispersion forces are the type of intermolecular force experienced by nonpolar substances, either nonpolar atoms or nonpolar molecules. Now, it's easy to understand why, if you have a molecule that is polar, that has a plus end and a minus end, how those molecules might start to stick together because opposite charges attract. The pluses on one side of a molecule will be attracted to the negative on a different side of a molecule. But why can nonpolar molecules or particles attract each other? That's a little bit more difficult to understand. So I'm going to start off with an example of helium. Now, helium has 2 protons and 2 neutrons in its center. And out in its electron cloud, it has 2 electrons in that cloud. Now, helium, He, is a neutral atom. It really does not stick very well to other helium atoms. That's why it's a gas. However, let me draw another helium here with 2 protons and then an electron cloud here with its 2 electrons. Now let's look at an individual helium atom. At any one moment in time, the electrons within this atom are all moving around, moving. There is a chance for one instant in time that both of those electrons are on one side of the molecule. If both of those electrons happen to, for an instant, be over on this side of the molecule, well, that makes this side of, I guess it's an atom, this side of the atom a little bit negative. And that's going to make this side of the atom a little bit positive, just because of chance, just because of probability. We have a dipole, 2 poles, for a moment. They're going to call that an instantaneous dipole, E-O-U-S, dipole. We have 2 poles for an instant. Now that instantaneous dipole is going to trigger an event in the adjacent helium atom. This helium atom has its 2 electrons whirling around it. Now, if this helium has a little bit positive side on the right-hand side of its atom, that's going to trigger a response in this helium because the electrons in this helium are going to be attracted to that partial positive charge. So they're going to come over to the left-hand side, and we will get a little bit negative on this edge of the atom and a little bit positive on this edge of the atom. Now, what we've done is this instantaneous dipole triggered or induced a dipole on the adjacent helium atom. Now, all of a sudden, just because one for a moment in time had a plus minus, we get a new one with a plus minus, and we know that opposite charges attract. So there's going to be this attraction between them. Now, they call that attraction a London dispersion forces. All nonpolar particles experience London dispersion forces. However, it's even more important than that. It turns out everything has electrons whirling around that we can shift a little bit according to an external electric field. Electrons within any atom can shift if one over here shifts because of probability. So not only do nonpolar particles experience London dispersion forces, but all particles experience London dispersion forces. So for nonpolar particles, that's the only type of force they have, but other particles which may have other forces will also experience London dispersion forces. Now, the last thing I want to talk about before we do some examples is how can I make London dispersion forces even stronger? So the thing is, helium has a very, very weak attraction to other helium atoms. That's why, again, it's a gas. But what if we didn't have 2 electrons that we can shift to one side for an instant? What if we had 4 electrons? 19 electrons, or something really, really big like iodine. If I pull out iodine, let me grab my periodic table here. Iodine has something like 53 electrons in it. The more electrons you have in that atom itself or in that molecule, the bigger this electron cloud is, then we can shift more electrons to one side and we can polarize it even more. The word that they use for the ability to polarize an atom or a molecule, that ability to make it polar is called polarizability. Ability to become polar. The more electrons you have, the more polarizable it is, and the stronger the London dispersion forces will be. The more electrons you can shift, the more negative and more positive sides those will be, and they will stick even harder. So when we're talking about London dispersion forces, if I ask you how to make them stronger, you're gonna look at the mass of that atom. How many electrons does it have? How big is that electron cloud? So let's go through some examples. If I ask you, let me go ahead and get my next paper. Who out of each of these two pairs of species, and everything here is nonpolar, who would have the greater London dispersion forces? You want to go ahead and look basically at mass, because the more massive it is, the more electrons it has, the bigger the electron cloud will be. So my first example is between xenon or neon. Which of those two, whoops, you can't see that. So let's go ahead and do it like this. Sorry. Between xenon and neon, who experiences greater London dispersion forces, the more massive one, xenon, will have stronger London dispersion forces, and that will be held together stronger. Now, out of chlorine and bromine, both of those are non-polar molecules. A Cl with a Cl, nobody wins the tug of war. A Br with a Br, nobody wins the tug of war. Both of them are non-polar and will experience London dispersion forces. Who's going to experience the stronger London dispersion forces between chlorine and bromine? The one with more mass. It gets more massive as we go down the periodic table. We have bigger electron clouds. So bromine will experience stronger London dispersion forces or stronger forces altogether. That actually is important because things like chlorine, well, chlorine is a gas. It's not held together very strongly. But as we go down the periodic table, bromine, even though it has London dispersion forces, which tend to be weak, bromine happens to be a liquid. It's held together stronger than a gas. So again, look for your masses. Now, if I asked you who has stronger London dispersion forces, methane, CH4, or ethane, C2H6, look for more mass. So 1 carbon versus 2 carbons, 4 hydrogens versus 6, ethane is going to have stronger London dispersion forces. All right, last one, nitrogen, N2. If you look up the mass of nitrogen, 2 nitrogens, it happens to have a mass of 28. Versus if we go to krypton, krypton weighs a lot more than that. So krypton has more electrons, bigger electron cloud. Krypton will have more London dispersion forces. I hope that helps. I will mention there is one other way to make London dispersion forces stronger besides the number of electrons, which is the most important way. But the other way is greater surface area of those molecules. The more contact you can make, the stronger those forces are going to be. I hope that helps. Take care.